Hello everyone and welcome to Zach's super cool math tutorials. Today's lesson will be focusing on lines and planes and intersections of such lines using Cartesian equations and vectors. So question A asks us to create a vector parametric and the Cartesian equations for a plane containing three non-zero points of your choice. So basically what this question is asking us to do is create three different equations using three non-zero points that we pick. So first I'm just gonna pick three random points. So point A is like 5, 1, 2. Point B is 3, -1, 4. And let's do point C is 4, 1, 1. Okay. So let's start off by making the vector equation. So the vector equation is defined by the equation r equals PO, which is the point given, plus T d1. And since this is a plane, there's going to be two direction vectors. And that's the second direction vector. And T and S can be any real number because these are just scalar factors that are going to stretch or compress our direction vectors. So that's what we're working with right now. And now we need to find out what direction 1 and direction 2 with these vectors equal to. And one very simple method to do that is, since we have these 3 points, we can get the slope of two sets of different points, and those are going to be our two direction vectors. So let's just pick line AB and line AC. It doesn't matter which ones you pick or in which order, as long as you're picking two different sets of points. So AB, to get the slope of that, we just to get the direction vector of that, we just do B minus A. And same goes for AC, C minus A. So point B would be 3, -1, 4, minus point A, which is 5, 1, 2. So which equals 3 minus 5, that's -2. -1 minus 1, that's -2. 4 minus 2, that's 2. And since this is a direction vector, much like you would a fraction, you can actually just simplify this. And usually with direction vectors, you want to keep the leading x value positive. So we're just going to divide everything by -2. So that would just be 1, 1, -1. So that is our simplified direction vector. And we do the same thing for C minus A. So 4, 1, 1, minus 5, 1, 2. 4 minus 5 is -1. 1 minus 1, 0. And 1 minus 2, -1. And then since we do want to keep these, we do want to keep the x value positive. You don't have to, but just for notation purposes, we could just multiply everything by -1. So that would just be 1, 0, 1. Spells out LOL. So let's just double check. 3 minus 5, -2, -1, minus 1, -2, 4 minus 2, 2. Okay. So now these are two direction vectors, and the only thing we're missing right now is the point given. So that is the point given. And luckily, we actually have 3 points that we're given. We're given A, B, and C. So we can pick any of these to plug into the equation, and it'd be correct. So I'm just going to pick point B. So the final equation would be R equals, point B is 3, -1, 4, plus T. Let's do 1, 1, -1, plus S. Now it doesn't matter in which order you put these, as long as you put them, because these are just variables that compress or stretch the direction vector, so it doesn't matter in which order as long as you're putting them in the first place. So that is our vector equation. Now the next equation that we have to write is the parametric equation. So I'm just going to draw a line over here. So the parametric equation basically follows this format. It's basically the vector equation split into its x, y, z components. So it would look something like, so the x would look something like the point given, but the x value of the point given, plus t times the x value of the direction vector plus s times the x value of the second direction vector. And the same pattern will continue, so POY plus T D1Y plus SD 2Y Z would equal to POZ plus T D1Z plus S D2Z. And so basically all we're going to do is look at the vector equation, and we're going to split it into its x components. So first we get x equals POX, so the point given, so the x value, which would be this right here, 3 plus t times the x value of the first direction vector, which is this, so x value would be 1. So that's just 1t, so we can leave it like that, plus s times the x value of the second direction vector, that's just 1, so we can just leave that as 1s or s. Same thing for y, the y value is -1, so -1 plus td1, so direction vector 1, the y value is 1, so we'll see that as t, plus s, the y value of s is actually 0, so you can write plus 0s, but obviously we're just going to simplify that to just -1 plus t. And now for the z value of p of the point given is 4, so z equals 4, plus the z value of the first direction vector, which is -1, so I'm just going to write minus t, and the s value of the second direction vector, or the z value of the second direction vector, which is 1, so it's plus s. So this would be the completed, let me just erase that. So this would be the completed parametric equation right here. And then now lastly, we'd have to make the Cartesian equation for this. So running out of space, I'm just going to write it over here. So the Cartesian equation, So a Cartesian equation is defined by the equation ax plus by plus cz, and this is for a plane, plus d equals 0. Now the normal of this Cartesian equation is going to be a comma b comma c. That's the direction vector. And then the point given for this Cartesian equation, which is just the point that exists on this graph, is going to be x, y, z. And then d is just some constant present within the Cartesian equation. So to get the normal, we already have two direction vectors, and to get the normal we could simply cross the direction vectors that we initially got, and that would give us the normal, because if you think about it, the normal is perpendicular to the plane. So we would start from here, the normal would have to be perpendicular to both, so it would be going upward like that. So it would be 90 degrees in both directions. And when you think about a vector that's perpendicular to two other vectors at the same time, that's simply just the cross product of two vectors, which equate this vector right here. So that vector is actually the normal. So to cross them, we know that our first direction vector is 1, 1, -1. So it is 1, 1, -1. So anytime you want to cross two vectors together, simply write the direction vector twice. So 1, 1, -1, 1, 1, -1. It'll make sense in a second. 1, 0, 1, that is our second direction vector that we got. So 1, 0, 1, 1, 0, 1. Now the first and last column of the matrix is what you want to remove. So just remove those. And now what you're left with is these the series of numbers where you can actually cross them together to get the cross vector. So 1 times 1 is just 1, and negative 1 times 0 is 0, so 1 minus 0. Then negative 1 times 1 is negative 1, and 1 times 1 is 1, so negative 1 minus 1. And lastly, 1 times 0 is 0, and 1 times 1 is 1. So that's the vector, and we can simplify this to 1, negative 2, negative 1. So this vector over here is actually the normal vector, and now we can simply plug this back in. If you recall, n equals a, b, c, and we have our point given, x, y, z. We have 3 points to choose from, so all we have to do is substitute the normal that we got, and any one of these points could be a, b, c. I'm going to pick c for this video. It could be any one of these points. Solve for the d value, and there's your full Cartesian equation. So let's do that right now. So what would happen is you would get ax plus by plus cz plus d equals 0. N is 1, negative 2, 1. And we said the point we're choosing is c, so 4, 1, 1. Let's write that there. 4, 1, 1. Yep. So 1 times 4 plus negative 2 times 1 plus negative 1 times 1 plus d equals 0. So 1 times 4 is just 4. Negative 2 times 1 minus 2. Minus 1 plus d equals 0. So 4 minus 2 is 2. Minus 1 is 1. So 1 plus d equals 0. So d is negative 1. Now we just rewrite the Cartesian equation using the normal. So it would be, remember, ax plus by plus cz plus d equals 0. And the normal was 1, negative 2, negative 1. So that's just 1x or x. 1 is 2y plus z. D equals negative 1 equals 0. So that is our Cartesian equation. So that's done for that problem. Okay. So our vector equation is right here. Our parametric equation right there. And our Cartesian equation. So for the vector equation, all we did is find the 2 direction vectors by finding the slope of 2 sets of points, and then we could use those as the direction vectors. And we picked one of these 3 points that we assigned as the point given. Any one of them, it doesn't matter. Next, we moved on to the parametric form, where we split the vector equation into its x, y, z components. So all we're doing is taking the x, y, and z value of each bracket basically, and we're inputting it into the equation. And then lastly, we moved on to the Cartesian equation, and basically what we're doing here is we need to find the normal for the Cartesian equation, and we're doing that by taking 2 direction vectors, so the ones we already found, crossing them together, and that would result us getting the normal. And then we know that the Cartesian equation is ax plus by plus cz plus d equals 0. We're plugging in a, b, c as a normal, and we're plugging in 1 point as x, y, z, solving for the constant d, and then plugging that all back in to get the Cartesian equation. Now next, create a Cartesian equation of a plane parallel to the one from part A. So if we go back to lines that you might have learned in early high school, grade 9, maybe even grade 8, you'll know that 2 lines that are parallel have the same slope, but just a different c value, ax plus y equals mx plus b, right? So it has a different b value. So for example, this might have a slope of 2, and this also might have a slope of 2, but this is actually being shifted up 5, and this is not being shifted up at all. So this might have a b value when you think about the equation mx plus b. This might have a b value of 5, and this has a b value of 0. So really the only thing we need to do for this problem is make sure that we have the same normal in the same line, but just shifted someplace else. So same direction vector, so same normal, different d value. So we can just rewrite the Cartesian equation we got up top, x minus 2y plus z. But instead of minus 1, we can pick any other number. We'll just pick minus 2 equals 0. So this is parallel to the plane created up there. Now C. Create a Cartesian equation of a plane that coincides with the one from part A. Now the key word here is coincides, and what coincides means in mathematical terms is basically when a line or plane lies on top of each other. So if you have this line over here, imagine creating another line that lies exactly on top of it. So this is actually two lines on top. It's two lines on top of each other. So one way we can do this is just to get the first plane that we made, x minus 2y plus z minus 1 equals 0. And we could just multiply this entire thing by a factor of 2. And this would technically still be the same line if we were to graph it, just multiplied by a factor of 2. And these would be directly on top of each other. So we'll just multiply by a factor of 2, and that would get us 2x minus 4y plus 2z minus 2 equals 0. And if you were to graph these planes, so two planes, they would be directly on top of each other. So that is the final answer. Okay, D. Create a Cartesian equation, ax plus by plus cd plus z plus cd plus d equals 0, using the rule below, where a equals your birth month, subtract 10, your birthday. Okay, so this is just basically us creating a custom Cartesian equation. So I'm just going to use my birth month for these examples. So a equals your birth month, subtract 10. So my birth month is March, so that's 3. Subtract 10 minus 10, which equals negative 7. B equals your day of birth, subtract 15. I was born on March 12th, so 12 minus 15 for 3. C equals negative 1. And D equals your favorite number. So my favorite number is actually 69. Okay, so you might recall that a Cartesian equation is in the format ax plus by plus cz plus d equals 0. And we have all of our variables. Now we just need to plug them in. So a is negative 7x plus, I should say minus 3y minus z plus 69 equals 0. And since we always want to have that x value positive, although it's not really necessary, just for the notation, I'm just going to multiply this by negative 1. So we would get 7x plus 3y plus z minus 69 equals 0. So that is the answer. Now solve for the intersection of the three planes from part A, C, and D. So part A, the Cartesian equation was x minus 2y plus z minus 1 equals 0. Okay, now from the start, we could already see that these two are exactly the same. So we could just pick either or to use. I'm just going to pick the first one, so we can completely just erase this. So this system of equations just turns into two different equations we have to solve for instead of three. We could just start off by subtracting the two equations, and we can get rid of the z variable. So x minus 7x, negative 6x, negative 2 minus 3y, negative 5y, z minus z cancels out, negative 1 minus negative 69, so negative 1 plus 69, that's positive 68, equals 0 minus 0, which is 0. So that is our first equation. Okay, that is our first equation that we can use. And now we have to rearrange this equation in terms of some variable so that we could solve for the other equation. So we have negative 6x minus 5y plus 68 equals 0. So I'm just going to solve for y in this case. So we'll just move everything to their side. So negative 5y equals 6x minus 68. So y equals negative 6 over 5x. Negative divided by negative is positive, plus 68 over 5. Okay, so that is our y value. And for this part of the step, we have to set one of the variables equal to t. So we're just going to set z equal to t. And the reason we do this is at some point of the system of equations, we're going to get the same variable expressed in each of these equations. So we could just, instead of saying x, for example, we could just set this variable to one common variable. For example, you might get like x equals 5y plus 3, y equals y, z equals 7x plus 4y. So this same variable y is always being expressed, and that variable y is actually the direction vector. So instead of writing it as y, we can just write it as t. So let's just erase all that. Now that we've got the value of y, we have to plug this back in to solve for the value of x. So let's just plug this back into the first equation. So x minus 2 times negative 6 over 5x plus 68 over 5 and plus z, but remember we set that to t, plus t minus 1 equals 0. X plus 12 over 5x, so x is just 12 over 12, or 5 over 5x. So 5 plus 12 is 17. So this is 17 over 5x. Negative 136 over 5 minus 1. That's the same thing as negative 5 over 5. So that would be negative 141 over 5 plus t. So now we must isolate for x. And the first thing I'm going to do is I see this common denominator of 5, so I'm going to multiply this whole thing by 5. So that gets us 17x minus 141 plus 5t equals 0. And then we're going to bring everything to the other side. So 17x equals 141 minus 5t. And now isolating for x, we get x equals 141 over 17 minus 5 over 17t. Alright, so that is our x value. Our z value, z equals t. And now we need to solve for our y value by plugging in whatever we got for x into it. So y equals negative 6 over 5x, but x is actually that value above, so we'll just put that in there. 141 over 17 minus 5 over 17t plus 68 over 5. Oops. Plus 60 over 5. $62 over 17. We're adding these two, by the way, plus 6 over 17t. So y is equal to this. So let me just rewrite this again on this corner right here. So we got x equals 141 over 17 minus 5 over 17t. and then we got y equals 62 over 17 plus 6 over 17t. And of course we said z equal to t. So now if we wanted to rewrite this into its vector equation, so we can properly visualize in 3D what that might look like, we can simply just take the x values, y, and z values of each variable. So r equals 141 over 17, comma 62 over 17, comma 0, because there's no point here, so it's just 0, plus t, x value of t is negative 5 over 17, 6 over 17, and 1. So that is the line of intersection that these three planes, or two planes technically, make. And if you were to try and imagine this on a 3D graph, for example, so this would be x, y, and z. You can, for example, this isn't to scale, but you can imagine one plane. Let me pick a different color. You can imagine one plane going like that, and another crossing in like that. So this line, this is where the plane intersects. So all of these points that exist on this line satisfy the variables for each equation. So this line over here, the vector equation, would equate to this right here. Create a vector equation of a line in 3D space using 2 points A, B, C, and D, E, F created where A, B, C, D, E, F are any positive or negative integer, but not a 0. Okay, so this question is basically just asking us to create a line in 3D using 2 points of our own choosing that is positive or negative, but not 0. So I'm just going to create A, 3, 4, 5, and since it must exist in 3D space, you'll notice I put an X, Y, and Z component to the point. And now B is just 6, 7, 8. So there's 2 random points in 3D space. Now we want to create a vector equation, and recall that the formula for a vector, or the equation of a vector equation, is PO, that's a point given, plus T D. And since this is a line that we're creating and not a plane, there's no need to create a second direction vector since we're only describing one range of motion. So the point given, we can choose either A or B. I'm just going to choose A. So the equation would be R equals 3, 4, 5 plus TD. Now the only thing left to do is solve for the direction vector, and we can do this by solving for the direction vector of line AB, which is equal to B minus A, it's equal to 6, 7, 8, minus 3, 4, 5. So 6 minus 3 is just 3, 7 minus 4 is 3, 8 minus 5 is 3. And this can be simplified to just 1, 1, 1. So our finished vector equation for such a line would be 3, 4, 5 plus T 1, 1, 1. So that was the finished vector equation for a line in 3D space. Now the final question asks us to solve for the intersection of the line created from part F with a plane from part D. So line created from part F is this right here. One, and the plane made from part D is 7x plus 3y plus z minus 69 equals 0. 7x. Now the way you want to solve this question is to actually convert this vector equation that we made into a parametric equation where we have the x, y, z components, and we can actually plug those x, y, z components into this Cartesian equation below. So we're just going to convert this into its x, y, z components. So x equals the point given at x, so that's 3 plus t. Y equals 4. I don't know why it's glitching. 4 plus t, and z equals 5 plus t. And the reason I'm writing t is because this is just 1t. I'm just writing it as t to simplify it. And now that we have the value of each of these, we can take each of these x, y, z values and plug them back into the Cartesian equation. So that would look like 7 times 3 plus t plus 3 times 4 plus t plus z, so that's plus 5 plus t minus 69 equals 0. So that'd be 21 plus 7t plus 12 plus 3t plus 5t plus t, or plus 5 plus t. Too many t's. Equals 0. So 20. So we're gonna start off by grouping all the like terms. So 21 plus 12, that's 33, plus 5, it's 38. 38 minus 69. Now we'll group in the t's, so 7t plus 3t, that's 10t, 11t, so it's plus 11t equals 0. So 11t equals 31, bring up the other side, and then t equals 31 over 11. So now we want to find the intersection of the line with the plane, and the way we can do this is by looking back at our parametric equation. We can simply sub in the value we got for t and the x, y, z formation, which would actually create a point, and that is a point of intersection. So the value of x, y, and z, we can put that as a point, and that will be our final answer. So we can rewrite that as x equals 3 plus 31 over 11, y equals 4 plus 31 over 11, and z equals 5 plus 31 over 11. So let's plug that into the calculator. So our final point of intersection would be 64 over 11, comma 75 over 11, and comma 86 over 11.